Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about regression trees, which are a very useful model because they can capture nonlinear dependence in an interpretable way. First, we will showcase why it is important to capture nonlinear dependence in a real-world dataset, and then we will explain how to build regression trees and fit them to data. Let's get to it. We're going to talk about regression trees, which are models for regression. Remember that in regression we want to estimate a quantity of interest called the response from multiple observed quantities that we call features. From a probabilistic point of view, if we want to minimize the mean squared error, as we saw in previous videos, the optimal estimator is the conditional mean. You cannot do better than the conditional mean of the response given the features if you just care about minimizing the mean squared error, which is a very reasonable metric. So what is the catch here? The catch here is that it is in general intractable to compute the mean square error due to the curse of dimensionality, as we have explained in previous videos. A short summary is that unless you have a very small number of features, there's going to be so many possible configurations of features that you're not going to be able to approximate the conditional mean from a reasonable finite data set most of the time. You will encounter at test time, when you try to apply your model, you will encounter different configurations of features than the ones you have seen in the training set. So that's what makes regression difficult. Because of that, we need to make assumptions when building regression models. And a very popular assumption is linearity. We have several videos where we talk about linear regression models. These models can be super useful, but today we're going to see that they also have some limitations. In a linear regression model, the response, which we denote by y, is approximated as a linear, or rather a affine function, because we have additive constants, of the features x. So we're approximating y as a linear combination of the features governed by these linear coefficients that we learn from the data and this additive constant that we also learn from the data. Consequently, if you realize, if the linear coefficient is positive and we fix all other features, if we increase the ith feature, the response is going to increase monotonically, like proportionally to that feature. If the linear coefficient is negative, as we increase the ith feature, if we fix everything else, the response is going to decrease proportionally to that feature. That is, and that is true for all the features in a linear regression model. Now we're going to use a real-world example to see that this can introduce some limitations when modeling real data. So in this example, we want to estimate the temperature in Manhattan, Kansas, and we're going to just have two features. One is going to be the hour of the day, which we're going to represent with a number from 0 to 23. So 0 is midnight, 23 is 11 at night. And the other feature is the day of the year. From 1 to 365, we're going to assume that we don't have a leap year. 1 is January 1st, 365 is December 31st. From these two features, we want to estimate the temperature in Manhattan, Kansas at that time. The training data is going to be temperatures from 2015, and our test data is going to be temperatures from 2000. So did I say 2016? The training is from 2015, and the test is from 2016. So it's quite important that you understand the structure of the data for the point I'm going to try to make in a moment. So let's take some time to take a look at the data a little bit carefully. So this is all the training data. In this axis is the first feature, which is the hour. In this other axis is the second feature, which is the day. And we have color-coded the response so that high temperatures are white and low temperatures are darker, okay, and the lowest are black. So when the day of the year is 0, that means that it's the 1st of January. so basically this means that these days are the winter, then these days are the spring, approximately, these days are the summer, and these days are the fall, and maybe the beginning of the winter a little bit. And as you can see, it's warmer in the summer, a little bit less warm in the spring, less warm in fall, and the coldest season is the winter. So that makes a lot of sense. If we look at it the other way, let's look at the other feature, which is the hour. This is midnight, so basically this is the night, this is the morning, this is the day, and this is the evening. Okay, so hopefully that makes sense. As you can see, temperatures tend to be higher during the day, in the morning, than at night, which again makes a lot of sense. And our goal is to learn a model where you just give it these two numbers, the hour of the day and the day of the year, and it gives you a reasonable estimate of the temperature in Manhattan, Kansas at that time. That's what we want to achieve. The test data, as you can see, has a very similar structure. It's colder in the winter, and kind of in the fall, warmer in the summer, less warm in the spring, and then it's colder at night than during the day. Okay, so very similar structure, but maybe I'm going to go back and forth a bit so that you can see that the actual values are different. Okay, maybe I should have erased these orange lines, but hopefully you get the idea. If we fit a linear regression model to those data, to the 2015 data, minimizing the squared errors, so basically this is the ordinary least squares estimator. If you want to learn more about that estimator, we have a whole video on it, and several videos analyzing the properties of linear regression models. If we do that, if we fit a linear model to those data, this is the model that we get. So we get that the temperature is proportional to the hour and proportional to the day with relatively small constants, and then we have this additive constant. So if we fix the day, the model says that the temperature just grows with the hour, and if we fix the hour, the model says that the temperature just increases with the day. And that's the model that we get. So maybe take a moment to think about whether you feel that this model is going to provide a good fit to the data, either visually or think a little bit about it. And the answer is no. The model is actually pretty bad. Why is it pretty bad? Because here the response increases or decreases proportionally. In this particular case, it increases proportionally to each feature, and that's not great for the kind of data that we have. Maybe I'll take a moment to go back to our data. This is the training data. Oops, I almost dropped my pencil. I'm going to erase all of this stuff. So here you see the training data. So what happens? Oops, I don't know what happened there. Okay. So what happens if we fix the hour of the day and we look at the dependence with the day of the year? So it is true that here, in general, as the day of the year increases, the temperatures increase. That is true. And the model, a linear model would capture this correctly. The problem is that in this second part of the year, the opposite is true. The temperatures start going down. So the linear model cannot capture these two trends at the same time. The same happens during the day. In the morning, it's colder, and then it gets warmer. Or during the night, it's colder, and as the morning arrives, it gets warmer. But then later on, as the day comes to an end and it's the evening, it starts getting colder again. So there's an increasing trend if we fix the day of the year. There's an increasing trend at the beginning as we increase the hour, and then there's a decreasing trend as we increase the hour further. And a linear model just cannot capture this structure. As a result, our linear regression model has pretty bad training error. So this is the square root of the sum of all the squared errors, the average squared errors. So roughly we get an error of 10 degrees and a test error that is on the same order. So basically we're not able to fit. The model is severely underfitting. We cannot fit this nonlinear structure that is present in the training set, and because of that, we also don't generalize to the test set. So this model just is not complex enough to capture the structure in the data. We need to learn a nonlinear model in order to obtain a good estimate. How can we learn a nonlinear model? Well, let me show you a possibility. We could think of cutting up the feature space into regions. This is what that would look like. Okay, we will see in a moment how we can learn those regions from the data, but for now, let's assume that we have been able to cut the feature space into regions, and then we can assign a constant estimate to each region. This would look something like this, where here in the summer, we're saying it's hot. We're saying that here at night in the winter, it's cold. During the fall, it's cold also. At night in the summer, it's it's warm, but not as warm as during the day, and so on and so forth. This enables us to implement a nonlinear estimator that is not constrained in the same way the linear estimator was, to always have to grow proportionally or decrease proportionally to each of the features. In the rest of the video, we're going to learn how to build such an estimator, but first let me show you that indeed it works much better. It achieves a training error that is half the training error of the linear model, and it generalizes well to the test set when we apply the model on the 2016 data. Okay, so now you're probably wondering two things. First, how do we compute these constant estimates? And second, how do we choose the regions so that we get a good model? So let's answer these two questions one by one. First, we're just going to assume that we have somehow learned the regions, and we're going to decide how to perform this estimate in each of the regions. So consider a certain region R that contains some of these data points, in particular contains NR data points. What we're going to do is we're going to minimize the sum of squared errors, which is an approximation of the mean squared error of our estimator for the data points that fall into that region. And we have decided that our estimate within that region is going to be a constant. So for all those points, they're going to have the same constant, and we want that constant to approximate their responses as well as possible. Okay, remember that the xi's here are the features which determine that the data belong to region R, because that's what we're doing. We're cutting up the feature space into disjoint regions that cover all of it. It's a partition. And then what we really want to do is approximate the response corresponding to those features as well as possible using a constant estimate. So let's minimize this function as a function of alpha, right? So we want to choose the constant in that region that is going to give us the best estimate for the response. How are we going to do this? Well, we have this function. We want to minimize it with respect to alpha, so let's take derivatives. This is the first derivative with respect to alpha. It's useful to realize that because this is a constant and we're summing over all the data that belong to the region R, this is just equal to NR times alpha, and here we have the sum of all the responses. If we take the second derivative, we realize, with respect to alpha again, we realize that it's positive, so this function, as a function of alpha, looks like this. And the minimum is going to be wherever the first derivative is equal to 0. If we set the first derivative equal to 0, boom, we get that the minimum is achieved at the average of the responses within that region. Does this come as a surprise? It should not come as a surprise if you remember our analysis of the mean as the constant estimator that minimizes the mean squared error. So if you want to approximate a random variable in terms of mean squared error and you have just one number to choose, you should choose the mean, as we showed in the video on, I think, the mean square and the variance, I think in that video. And this is also true when we go to a data set. If you have a data set and you want to approximate it in terms of residual sum of squares, which is an approximation to the mean squared error with a single number, then you should use the mean. This is the ordinary least squares estimator if you're just allowed to use one constant. Okay, so this should not be surprising. If you have already your regions, the way you get the best constant estimate in terms of squared error is by just taking the average within each region. And that's how we obtain this estimate here, which does really well for our data. So now we've gotten to the most difficult question, which is how do we build these regions in order to approximate the response of interest as well as possible? The problem that we have is that there's just too much flexibility. There's so many possible regions, especially if you have more than two features. We have an example with two features so that we can visualize everything and understand everything, but typically you will want to consider 50, 100 or even more features. So in that case, the possible regions that you could choose explode exponentially. So there's no way we could consider every possible region. Instead, what we can do is use a binary tree to represent the regions, and that's why regression trees are called trees, because we use a binary tree to represent these regions in which we have our constant estimates. Let's take a look at how that even works, and then later on we will worry about how to actually build the tree. So basically, here, each bifurcation of the tree tells us how we're cutting up the feature space. So here, these two branches correspond to D, which is the day of the year, smaller than 65 and larger than 65. So here this node would correspond to this region, and this node would correspond to this region. And then in the tree, we continue splitting some of the nodes according to one of the features. And it's always according to one of the features. So here, it's again according to the day. So we're splitting this node that we had here that corresponded to this region. We're splitting it using again the day according to whether the day is below or above this threshold equal to 296. Again, we split according to the day, and in this case we split here, and we're splitting this node. So we're splitting this region here according to whether the day is below 144 or above 144. And finally, we split this region here, which was here, according to the hour, according to the other feature, depending on whether the hour is above or below a threshold of 8. So maybe as a summary of this, let me show you that the leaves of the tree provide a partition of the space. So the first subset of the partition is if the day is smaller than 65, okay? Those are basically the winter nights. No, sorry, the winter days in general, days and nights. Sorry. As you can see, we're not splitting according to the hour. We have a very small tree here so that I could kind of show it to you in detail. Then we have another node here where the day is larger than 296. Okay, so this is the fall. Now we have another node here where the day is between 65 and 144. So it's this guy. Now it gets more complicated. We're just left with those two regions. One corresponds to when the hour, so the day is between, let me get this right, 144 and 296, and the hour is below 8 or above 8. Okay, and this is the partition that is induced by this tree. Okay, so hopefully that makes sense how the binary tree is connected to this partition of sets where we produce constant estimates. And that's our regression tree. So hopefully this allows you to visualize it. And then of course we average in each of these regions in order to obtain the estimate produced by the regression tree. So now imagine that it's August 19 at 3 a.m. and you want to estimate the temperature in Manhattan, Kansas. So August 19 corresponds to D equal to 251 and 3 a.m. corresponds to H equals to 3. All right, so what do we do? Well, first, D is greater than 65. Boom, we go down that branch. D is smaller than 296. We go down that branch. D is larger than 144. We go down that branch. And now H is smaller than 8. So our estimate is 19 degrees. As you can see, our estimate is interpretable. We know exactly why we are producing that estimate of 19 degrees. It's because, the feature D is between 144 and 296, and the feature H is smaller than 8. So this is an interpretable model which can be very important for some applications. When I was coming up with this example, I wasn't in Manhattan, Kansas. I was in Manhattan, New York. But I looked up online what the temperature was in Manhattan, Kansas, and it was 22 degrees. This was 2023. So the estimate was not too bad. Okay, so now how do we build this tree? We have seen that we can represent this partition of regions as a tree, but how do we choose the tree, or equivalently the partitions, to fit the data well? Well, we can just choose the tree that best fits the training data in terms of, for example, the residual sum of squares. That's a very reasonable thing to do. But here we encounter, a problem that is similar to the one that we thought about before when we were considering all the possible regions. There's just a lot of trees. So imagine a tree with depth h and 2 to the h leaves. So just to be clear, this would be a tree of depth 0, a tree of depth 1 has 2 leaves, a tree of depth 2 has 4 leaves, and so on and so forth. Now, in order to decide all of the splits in this tree, we have to first choose according to what feature we're going to split in each bifurcation, and then we're going to have to choose the threshold for that feature. But let's take a look at how many bifurcations there actually are. So here we have 1 bifurcation, 2 bifurcations, 3 bifurcations. So it turns out that if we have depth h, the number of bifurcations is going to be 2 to the h minus 1. And you can check that for my small example. This is true because 2 to the 2 is 4 minus 1 is 3. Okay, and we saw 3 bifurcations here. And you can see that this is also true for larger trees. This is problematic. Why? Because the number of possible trees is the number of bifurcations multiplied by the number of features multiplied by the number of thresholds, because that's the decision that we need to make. Those are all the possible decisions that we need to make in order to build the tree. So if you consider that, then we would have d times t to the b, because you can make the different decisions in different bifurcations. For example, if the depth of the tree is 4, the number of features is 10, and the number of possible thresholds is 100, which is quite conservative. This is just like a regression problem with 10 features. It's, if you have continuous value features, 100 is not a crazy possible number of thresholds, and the depth of the tree being 4, that's actually a pretty small tree. The number of possible trees that we have is 10 to the 45, so completely insane. There's no way we're going to be able to consider all of them, even if we had all the time in the world. So it's just intractable to consider all the possible trees. So what can we do? Well, what we do is we are greedy, which has a negative connotation, but is often very useful in data science. We're going to just add 1 bifurcation at a time, the bifurcation that is best according to the fit to the data, even if that means that we're not going to get the best possible tree at the end of the day. At least we will get a tree, which is better than no tree. This method has a pretty intimidating name, which is recursive binary splitting, because you're splitting the nodes in the tree recursively. But even though it sounds intimidating, it's actually kind of simple. So let's take a look visually at how this works, and then we will dive a little bit deeper into one of these decisions to see exactly how the decision is made. So first, we have all the data, and we realize that the best thing in terms of fit to the data, if we just want to consider one bifurcation, is to split the regions according to the day of the year and to use this threshold. Again, in a moment, we will see how we actually decide this. And now we're left with two regions. So now we have to decide which region to split according to which feature and according to what threshold. And what we decide is that, this is the corresponding tree. So the threshold is 65 and the chosen feature is D. And we can get the corresponding estimate by just averaging in the two regions. Now we want to grow the tree further, so we have to decide whether we want to split this node or we want to split this node, and according to this feature or this feature, and which of the possible thresholds do we want to use. And it turns out that this is the best split. It's best to split according to the day and to split here. And this gives us this tree that now has 3 leaves instead of 2, corresponding to these 3 regions. Now, we do that again. We need to see which of these 3 regions to split, according to which feature and according to which threshold. And it turns out that it's best to split this middle one, again according to the day of the year, and to use that threshold. And this gives us this tree, which now has 1, 2, 3, 4 regions corresponding, that you can see right here. And now let's dive a little bit deeper into how we make this decision. We have 4 regions, and we want to decide which one of them to split according to what feature and according to what threshold. What we're going to do is we're going to minimize the residual sum of squares, which is exactly, by the way, the same cost function that we use when we are fitting an ordinary least squares model, except that this model is able to be nonlinear, whereas the ordinary least squares model is constrained to be linear because we're just learning these linear coefficients that multiply the features. Okay, so now we are minimizing the residual sum of squares. Imagine that we already have m regions. In our example, we have 4 regions. The estimates for each region are these alphas, which are obtained by averaging the training data within each region, as we discussed earlier. And now the residual sum of squares of the whole tree is basically the sum over each region of the squared error for the responses of each data point in the corresponding region. Okay, so for the first region, we sum all the squared differences between alpha 1 and the corresponding responses. For the second region, we sum all the squared differences between alpha 2 and the corresponding responses, and so on and so forth. If we focus in one of the regions, we can separate actually this residual sum of squares into the residual sum of squares in each of the regions. And we want to choose a split, which basically means we're going to separate one of the regions. We can consider how this changes the residual sum of squares. It's obviously going to only change the term corresponding to that specific region. If we split the region RR into the subregions A and B, what's going to happen is that we used to have this term within here, which was the difference between the response for the feature vectors that end up in this region RR. This is what was in the previous residual sum of squares. Now if we split, instead of that, we're going to have the features are going to be separated into 2 groups, the ones that belong to A and the ones that belong to B. And we're going to re-estimate by averaging in the 2 sub-regions. We're going to re-estimate this constant and we're going to recalculate the residual sum of squares. So now realize that every one of these guys is going to go here or here, and instead of being compared, let's see if I can find, yeah, here. Instead of being compared to alpha r, they're going to be compared to alpha a or alpha b. Okay, this is what's going to happen. That's going to be the change in the residual sum of squares from the original tree where this region RR is not separated, and the new tree where region RR is going to be separated into region A and region B. We're going to have two such subregions for each region, feature, and threshold, right? We have to choose what region to split, according to what feature, and according to what threshold. But because of the fact that we're just considering one split, this is tractable. We can go and compute all the possible values of this change in residual sum of squares for each region, feature, and threshold. And let me show you exactly how we do that. We're going to choose, obviously, the split that maximizes this because we want the residual sum of squares to decrease as much as possible. We want the new one to be much smaller than the old one. So now we have our tree with the 4 regions that I showed you before, and we want to decide how to split. So we're going to compute this difference in the residual sum of squares for each of the regions. So let's start with the day of the year. Just to be clear, what we're doing here is saying, okay, what if we split the, let me try to draw this in a reasonable way. What if we split region 1 with this threshold and this feature and the day? So then we're going to get maybe this residual sum of squares. What if we, and then basically here you see all the possible changes here, all the possible changes in the residual sum of squares for region 1 and feature D, feature day of the year. The best one is using this threshold if we were going to split region 1 according to the day. But if you realize, so this would be region 2, this is region 3, and this is region 4. And what we observe is that the best thing to do in between the regions, if we're going to split according to the day, is to split region 3 according to this threshold. Okay, so roughly around here, I think it is. But now we haven't considered the other feature, right? Because we will have to choose which region to split, but according to which feature also. So now let's see if we separate the regions according to the hour instead of the day. And what we observe is that if we split region 4, 3, or 2, we don't see a decrease in residual sum of square that is larger than the one that if we split according to the day. But if we split region 3 according to the hour, and we split it at hour, I think it's around 6, so roughly here, then we do get a greater decrease in the residual sum of squares. So our greedy scheme is going to choose to split region 3 according to the hour and using a threshold of, I believe it's 6 or around that. Okay, so that's what that split looks like. So now we have added this, oh, it wasn't 6, it was 8. Okay, so we have added another split in our tree where the feature that we're using to split is the hour, and the region that we're splitting was this one. And that's what the final tree looks like. To be clear, this is alpha A and this is alpha B. Okay, now we have 2 separate averages within that region as we had explained. So this is the procedure that we use to build a tree by adding nodes one by one in order to greedily minimize the residual sum of squares. But where do we stop? Because of course, if we have a tree with 11 leaves, we can then consider a tree with 15 leaves, and it's going to fit the data better because we're just splitting regions in order to minimize the residual sum of squares further and further. So of course, we're always going to get a better fit if we keep adding leaves to the tree. But please take a look at the estimate that corresponds to the 15-leaf tree. think about whether there's something that bothers you about it, because there's definitely something that bothers me about this quite a lot. So think about it for a moment, maybe pause the video. What bothers me about this estimate is that if I look at this area here, this seems to be telling me that if I'm in the middle of the winter, it's going to be warmer than if I wait a few days, which is weird to me. If someone in February tells me like, oh, you know, wait a week or two and it will become colder, I'll be like, what do you mean? Like, I would expect it to become warmer, if anything, right? So what happens here? This is actually a reasonable thing for the tree to do, because in 2015, the temperature was indeed colder at that time, but these are just random fluctuations that occur year to year. So when we go to 2016 and we compare the two estimates when the actual temperature in 2016, what we observe is that here it was warmer than here. So we don't see the same pattern as in 2015. Basically, the tree overfits these fluctuations that occur in the temperature of 2015, which doesn't enable it to generalize as well to 2016. So eventually, the regression tree overfits the data, which will happen with every regression model, but it happens more with regression models that have more flexibility. And regression trees do suffer from overfitting quite a bit because they're able to zoom in by creating these subregions into very intricate into very intricate patterns within the training data. Let me show you the training and test error for for trees that have different number of leaves. The training error is here in black. It decreases continuously as we increase the number of leaves, which makes a lot of sense because we're just fitting the data better and better and better. But when we hit, I think it's 11 or between 11 or 12, after that, we see an increase in the test data because we're capturing these spurious patterns in the training data that are not reproduced in the test data. Okay, so what have we learned? We have learned how to build a nonlinear regression model that is interpretable using regression trees. And we have also learned that we have to be very careful about overfitting. And that's all I got. Thank you very much.